Imagine a time before time existed. This is the Planck Era, the universe's first fleeting moments after the Big Bang. It is a realm of unimaginable extremes where the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single, all-encompassing force. Named after physicist Max Planck, this era represents the ultimate frontier of our knowledge about the cosmos. In this strange realm, the laws of physics as we know them cease to apply, replaced by the bizarre and counterintuitive laws of quantum mechanics. By studying this era, we are essentially peering back to the very beginning of time, seeking answers to some of the most fundamental questions about our existence. The Planck epoch marks the very beginning of the universe as we know it. This epoch is named after Max Planck, the father of quantum theory, whose work laid the foundation for our understanding of the quantum realm. It is an incredibly brief period, lasting from the Big Bang at time 0 to approximately 10 to the power of negative 43 seconds later. This duration is so short that it defies our everyday comprehension, existing only as a concept in the realm of theoretical physics. This incredibly small number, known as Planck time, represents the smallest unit of time that has any physical meaning according to our current understanding of physics. It is a boundary beyond which the conventional laws of physics cease to apply and quantum gravitational effects dominate. To put this into perspective, if we were to represent the entire age of the universe as a single year, the Planck epoch would be shorter than a single blink of an eye. This comparison helps us grasp the fleeting nature of this epoch in the grand timeline of the cosmos. During this unimaginably short period, the universe was incredibly hot and dense. Temperatures soared to unimaginable levels, and the density of matter was beyond anything we can currently replicate or observe. The four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single force. This unification is a key concept in the quest for a theory of everything, which aims to describe all physical phenomena within a single framework. We cannot directly observe what happened during this time, as the universe was opaque to all forms of radiation. This opacity means that no light or other electromagnetic radiation could escape, leaving this epoch shrouded in mystery and accessible only through theoretical models and indirect evidence. To navigate the extreme conditions of the Planck era, physicists have developed a unique set of units known as Planck units. These units are essential for understanding the universe at its most fundamental level. Physicists use these special units to make sense of the incredibly small scales and high energies that were present just moments after the Big Bang. These units are based on fundamental constants of nature, such as the speed of light, the gravitational constant, and Planck's constant. By using these constants, scientists can create a system of measurement that is universally applicable, regardless of the conditions. Planck time, as previously mentioned, is one such unit, representing the smallest meaningful unit of time. It is the time it would take for light to travel one Planck length in a vacuum. But Planck units extend beyond just time. They also include measurements for length, mass, and even temperature, providing a comprehensive framework for understanding the universe at its smallest scales. There's also Planck length, representing the smallest measurable distance, and Planck mass, representing the smallest possible black hole. These units help scientists explore the boundaries of our physical theories. These units are incredibly small. For instance, the Planck length is so tiny that it is almost inconceivable, far smaller than the size of an atom or even a subatomic particle. The Planck length is about 10 to the power of negative 35 meters. To put that into perspective, it is a millionth of a billionth of a billionth of a billionth of a centimeter. When we get down to these incredibly small scales of space and time, our classical theories like Einstein's general relativity break down. This is because the effects of quantum mechanics become significant. This is where quantum mechanics comes into play, governing the behavior of matter and energy at the atomic and subatomic levels. By understanding Planck units, scientists can bridge the gap between the macroscopic world of general relativity and the microscopic world of quantum mechanics. In the Planck era, where the very fabric of spacetime was being stretched and compressed at unimaginable scales, quantum mechanics and general relativity collide. Quantum gravity suggests that at the Planck scale, spacetime itself is not smooth and continuous as described by general relativity. Instead, it is thought to be foamy and quantized, fluctuating wildly on incredibly small scales. Imagine space-time as a churning ocean. During the Planck era, these quantum fluctuations in space-time would have been so intense that they would have governed the behavior of all matter and energy. This intimate dance between gravity and quantum mechanics is a central theme in our understanding of the Planck era. One of the greatest challenges in modern physics is to find a single theory that can explain all four fundamental forces of nature. During the Planck era, the four forces are believed to have been unified into a single force. However, as the universe expanded and cooled, this symmetry broke down. The forces separated from one another in a series of phase transitions, much like water transitioning from ice to liquid to vapor as it heats up. First, gravity separated from the other forces, followed by the strong nuclear force. Understanding how these forces were unified and how they separated is crucial for developing a complete understanding of the universe's evolution. The Planck era was a time of unimaginable heat. The temperature of the universe during this time is estimated to have been around 10 to the power of 32 Kelvin. At these extreme temperatures, matter as we know it could not exist. Instead, the universe was filled with a sea of extremely energetic particles constantly colliding and interacting with one another. These particles were so energetic that they were constantly being created and destroyed according to the principles of quantum mechanics. Understanding the behavior of matter and energy under these extreme conditions is crucial for understanding the universe's early evolution. These extreme temperatures and energies had a profound impact on the evolution of the early universe. As the universe continued to expand and cool, it eventually reached a point where the temperature dropped below a critical threshold. This marked the end of the Planck era and the beginning of the Grand Unification Era. During the Grand Unification Era, the strong nuclear force, weak nuclear force, and electromagnetism were still unified into a single force. This transition was a pivotal moment in the history of the universe. It marked the first time that one of the fundamental forces, gravity, separated from the others. This allowed for the emergence of new particles and interactions, setting the stage for the formation of the universe as we know it. The Planck era, while incredibly brief and shrouded in mystery, holds immense significance for our understanding of the universe. It is the epoch where our current laws of physics break down, and where we must look to new theoretical frameworks, such as quantum gravity, to describe the behavior of matter and energy. Studying the Planck era is like trying to piece together a puzzle with most of the pieces missing. By understanding the Planck era, we can hope to answer some of the most fundamental questions about our universe. While the Planck era remains a profound mystery, it is a mystery that we are actively trying to solve. Although we cannot directly observe the Planck era, scientists are developing new ways to probe its mysteries. One promising avenue is through the study of cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates the universe. By analyzing the subtle patterns and fluctuations in this radiation, cosmologists can glean insights into the conditions of the very early universe, including the Planck era. On the theoretical front, physicists are working tirelessly to develop a complete theory of quantum gravity. String theory and loop quantum gravity are two leading candidates for such a theory. String theory proposes that the fundamental building blocks of the universe are tiny, vibrating strings. Loop quantum gravity suggests that space-time itself is quantized, meaning that it comes in discrete chunks. The Planck era represents the ultimate frontier of our knowledge about the universe. This epoch, occurring just fractions of a second after the Big Bang, is shrouded in mystery and intrigue. It is a time when the universe was incredibly hot and dense, and the laws of physics as we know them were not yet in place. It is a realm of extreme conditions and profound mysteries, where our current understanding of physics breaks down. In these extreme environments, phenomena such as black holes and neutron stars challenge our comprehension and push the boundaries of scientific knowledge. Yet it is precisely this challenge that makes the study of the Planck era so compelling. Scientists and astrophysicists are tirelessly analyzing data and developing new theories to unlock the secrets of this enigmatic period. Their work in research labs around the world is crucial to advancing our understanding. Future telescopes, such as the James Webb Space Telescope, will allow us to peer deeper into the universe's past than ever before. These advanced instruments will provide unprecedented views of the cosmos, revealing details that were previously beyond our reach. On the theoretical front, the quest for a complete theory of quantum gravity is one of the most active areas of research in physics. This theory aims to reconcile the principles of quantum mechanics with general relativity, providing a unified framework for understanding the fundamental forces of nature. Breakthroughs in this field could revolutionize our understanding of the Planck Era and the universe's origins. Such discoveries would not only shed light on the early moments of the cosmos but also have profound implications for our understanding of space, time, and the nature of reality itself. The study of the Planck Era is a journey into the unknown, a quest to unravel the deepest secrets of the cosmos. It is an exploration that takes us to the very edge of scientific knowledge and beyond, pushing the limits of what we can comprehend. The universe is full of wonders, and the Planck Era is perhaps the greatest wonder of all. As we continue to explore and discover, we inch closer to understanding the profound mysteries that lie at the heart of our existence.